Welcome back, and thank you very much for watching this lecture video. I want to practice a couple of more chemical reaction for benzene molecule. And so we are trying to replace hydrogen atom by some substituent. And the first reaction is going to be the sulfonylation. Technically, we are taking hydrogen atom on benzene molecule and replacing it by SO3H1 time. And the starting point of the reaction is going to be mixing sulfuric acid with sulfur trioxide. That's going to give us a very reactive electrophile, and that's going to be SO3H plus SO3H with a positive charge. And as you see, because sulfur it has a positive charge, this species is not going to be stable, and so it can attack the ring, or the ring it will share electron with it, and our ring it will be the nucleophile, or you can say the electrophile. It will attack the ring, and you can call it the electrophilic attack in that case. But from the ring side, you can call it nucleophilic. And so the bottom line, 2 electrons from ring will be shared with that electrophile, and we will get sulfur attached to oxygen. We have 2 oxygen and with double bond, and the third one it will have a single bond with sulfur, so that means it will have 2 lone pair, and last bond it will be attached to hydrogen. Now sulfur it will have 0 formal charge in this case. That means somewhere in the ring we need to have a positive charge, and that's going to be here. Now we need to have a base to technically restore this one, and the base it will be SO3. Okay, SO3 it will attack this. It will attack this acidic hydrogen, and those 2 electrons, they will be shared with the ring, and in that case we can restore the the benzene molecule. So after taking the H, we will get again HSO3 with a positive charge, and what else? We will get sulfur with 3 oxygen attached to the ring, and that's going to be the final product. Okay, so what was our base? The base was SO3, and SO3, we used it at the beginning to generate SO3H plus, okay? And next step, SO3 was used as a base to take hydrogen from the system and restore the aromaticity. Okay, next one is going to be the Fiedel-Crafts alkylation. And if you are dealing with a carbon that is a primary carbon, reaction is going to be really straightforward. First step, you will have a Lewis acid react with halide, and the halide it will be attached to the Lewis acid. Why is it attached to the Lewis acid? Because the Lewis acid has empty orbital. Okay, now final, the first product of this, you can say that we generate the chloride that attached to aluminum and carbon on the other side. So chloride has a positive charge. What does it mean? It means the chloride is going to be thirsty of electron, and it will pull good amount of electron from carbon. So that carbon is going to have a good amount of positive charge. Forgive me. So this one will have a positive charge. Now, our ring, it can share electron with that carbon, and it will kick the chloride out of the system. So very soon this is going to happen, and we will have the ethyl attached to the ring. But now we have a positive charge, and the positive charge it will be on this carbon. So we can restore the aromaticity by technically taking H from the ring, and the one that is going to do it for us, it will be aluminum with 4 chloride, because this one it will have a negative charge. And so this one will attack hydrogen, and after after generating this product for us, the alkylation product, we will get HCl, and next one, it will be the aluminum with 3 chloride. So this one will be really straightforward if your alkyl halide is a primary alkyl halide. So your carbon is a primary carbon. Now, what will happen if you have a secondary or tertiary? In that case, you might get a rearrangement. So you need to include that one in your calculation. Okay, so say in this case, we have a tertiary carbon. Okay, and so we have a tertiary carbon that is holding a chloride. And again, a chloride that will react with the aluminum chloride is a Lewis acid. And in this case, we get aluminum chloride plus we get a carbocation. We did not get a carbocation before. Okay, and if I go back, previous step, we didn't get a carbocation because this is a primary carbon. It will not be a stable carbon. I'm talking about this carbon. This is a primary carbon, and this one will favor technically SN2 reaction. And simply halide, the ring, it will attack that carbon. It will kick the chloride out of the system. And that's the reason, I said aluminum chloride with negative charge plus technically this intermediate. Okay, but here we have a tertiary carbon. And now when you react with the aluminum chloride, it will give us a tertiary carbocation. A tertiary carbocation is stable enough, and that's going to attack the ring. So now this one, okay, can attack the ring, or you can treat the ring as a nucleophile, and it will go after that carbocation, or the carbocation, it will go after the ring. And what do we get? We get this. We get tertiary butyl attached to the ring. So somewhere we're going to have a positive charge, and the positive charge, it will be there. Now, we need to remove that H to restore the benzene ring. And so the aluminum tetrachloride with a negative charge, forgive me, I wrote a positive charge here, is negative charge. This one is going to go after H, and it will remove that one. So now we will get a tertiary butyl attached to the ring, plus we get HCl, and next product will be the starting compound, which is aluminum chloride. So we got the tertiary butyl attached to the ring plus HCl and aluminum chloride, which was the starting compound. Okay, now we have a student that he's using this alkyl halide in the presence of aluminum chloride. First assign how many products we can get and which one is going to be the major product. So I'm going to say the first guess is we have primary carbon. This is a primary carbon. A primary carbon, it will be attached to the chlorine. And forgive me. We have a primary carbon, okay, and the chlorine on the primary carbon, it will attach the aluminum chloride, and it will create a positive charge. Now, because chlorine has a positive charge, it will pull electron density from carbon, and carbon will get a positive charge. Now, I can say that this one, it will attack. If this one attack the carbon, the product that we should get will be this. So we have carbon, primary carbon, and then that carbon attached to two more carbons. That's one possible product, or we might get this. Okay, let's say this one. Okay, this one is going to pull electron density from carbon, and we get this species. Okay, so we got a carbocation that is a primary carbocation. But if you look to the neighbor carbon, it has a hydrogen there. We can have 1 and 2 hydride shift. Okay, 1 and 2 hydride shift. And if this one happen, if this hydrogen move here, we will get such a carbocation. So hydrogen now, it will be here. Okay, and that carbocation now is going to turn to a tertiary carbocation. A tertiary carbocation is more stable than the primary, and that one, it can be, it can be the right electrophile to attack the ring. So if that one happened, then I might get this. Okay, so instead of attacking primary carbon, this time we will have a tertiary carbocation. And similar to the previous step, we get, again, positive charge here. And then we need to have a base. And our base, it will be aluminum tetrachloride. This one will go after hydrogen. It will take hydrogen from the ring. We'll take it out as H+, and it will restore the benzene and ring. So we will get a tertiary butyl here plus HCl plus aluminum chloride. Okay, so what's going to be the second product? The second product, we will have a tertiary butyl group attached to the ring. Okay, which one is going to be the major product? The major product will be this. This is the major product, and this one, it will be the minor product. So be careful. If there is a chance to do technically to turn a primary carbocation or secondary carbocation to a tertiary, okay, to a tertiary mechanism, or the reaction will follow that pathway, and it will try to create the most stable carbocation. And because tertiary is the most stable one, and so that's going to be the right electrophile and is the one that is going to attack the ring. So expect to get that one as a major product. Okay, last one that I want to practice. As I said, the downside of the Friedel-Crafts alkylation is we can have rearrangement. Is there any way to run the reaction without rearrangement? Yes, it's possible. And the way we do it this time, we're going to use a carbonyl group that's attached to the alkyl that we wanted, and plus we will have an halide attached to that ring. Now, the halide, we can get it out of the system. So if I take aluminum chloride and react it with this species, aluminum chloride, it will take the chloride, will turn to -1 here, plus we will get this species. Now, carbon has a positive charge. Is there any way to make a carbon more stable? Yes, oxygen is there, and oxygen, it can share lone pair with oxygen and with carbon, and it will make it more stable. So we can have this resonance structure, and we can have carbon attached to oxygen through a triple bond. Next, we'll have carbon there. This carbon, it will be, okay, let's see. 1, 2, 3, 1, 2, 3. Okay, yes. Now, oxygen, it has a positive charge. Okay, and this is going to be the electrophile that it will attack the ring. So we will have, technically, we will have a carbon that attached to oxygen through a triple bond. And now we will have this species. Ring, it will go after carbon, because carbon, it has a positive charge. Remember, here we have a positive charge. Oxygen does not want to have a positive charge. So the majority of the positive charge will be sitting on carbon, not oxygen. And if that one happened, you will have a carbon attached to oxygen. And next, you will have carbon here. Okay, we got this. Now we will have a positive charge there. We need to take the hydrogen to restore the ring. And the way we take it, again, is aluminum tetrachloride will get involved. It will go after hydrogen. We'll take hydrogen out, take hydrogen out of the system, and it will leave as HCl plus aluminum chloride. What else we get? We get this molecule. We get carbon, okay, directly attached to the ring. That carbon, it has a double bond with oxygen. Next, rest of the chain. And as you see, we have 1, 2, 3, 4 carbons there. So I managed to attach alkyl, like an alkyl group to the ring. That alkyl group, it has a carbonyl. Okay, you might say this is not alkylation. Yes, it's not just alkylation. Is alone is an acylation actually, and because it's an acyl group attached to the ring. And when I say acyl group, I'm talking about this. This part. This one technically got attached to the ring, and when we call it acyl group. Okay, so what's the benefit of this? The benefit of it, I managed to put alkyl group attached to the ring without being worried about the rearrangement. But I got a carbonyl. What should I do with the carbonyl? I do have access to a couple of methods to reduce the carbonyl group, turn it to alcohol, and the alcohol at the end, I can remove it from the system and make it saturated compound. And so I can get rid of oxygen and replace it by hydrogen atom. And that's one solution to attach the alkyl group without being worried about rearrangement. And this is going to be the end of this lecture. And thank you very much.